Now we're going to do problem solving. So thinking about how people work through problems and solve problems, and not even just simple things like 1+1 kind of problems, but also more complex problem solving decisions, like what to wear in the morning, or how to get through college, how to buy a car. So this sort of encompasses everything from sort of simple problems to bigger, more complex issues. So what is problem solving to start? How do we define such a complex task when we're talking about cognition? So a problem is a situation where there's no immediately apparent way of reaching the goal. So it's not simply, okay, my problem is 1+1 equals what? 2. So problems are things that have obstacles that arise that you have to solve to get to your goal. Okay? So you might have trying to get along with your roommate in college. You have emotional problems that you have to solve with your significant other, or the simple problem of what do I take next semester. So problem solving is anything where you have a problem and there's no like direct solution to reach the goal. Okay, so we have to overcome some sort of obstacle and to be able to get to a goal state. So a couple parts to problem solving. First is there is a goal state. This is the solution to the problem, and is the answer where you're trying to get to. The initial state or start state is where you are when you start. So that is like point A, and the goal state's point Q. So how do I get from A to Q? Those are my operators. And those are like mental ways to solve problems. We're going to talk about a couple types of operators. So there are ways that you can get from the start state or initial state to the goal state. So if you're trying to find a way to campus and one of the main roads is closed because there's been an accident, your start state would be when you figure out, oh no, there's an accident, what do I do? The goal state would be campus, and the operators would be new directions. So a couple types of problems that people use to study problem solving. So there are well-defined problems. These are problems where the initial state and the goal state are clearly defined. So I know where I'm starting and where I'm ending, and all the rules are also clearly defined. So it's called a well-defined problem because everything you're trying to do is well-defined. So the Tower of Hanoi is one of the experiments that you can take, and it's a well-defined problem. And it's a problem-solving task where discs are moved among pegs. So you have 3 pegs, 3 discs or more, and you're trying to move them from one peg to a final peg, but there are lots of rules. So here's an example. Up here on the top left, this is the initial state. Come on now. Okay. And I'm trying to get over here to this goal state. And then I have these specific operators. So I can only move one disc at a time from one peg to another. So I can move the smallest disc to peg 3 if I wanted. I can't move a disc at the bottom first, so it's got to be the top disc. And I cannot place a larger one on a smaller one because it'll smush it or something. So people try to solve this problem going from the initial state to the goal state, and we have to follow these operators, so no cheating. So here is the solution to the Tower of Hanoi, which you should look at and then immediately forget because you are going to take this as an experiment, but you've got to break it down into sub-goals. So I need that big disc to be free because it's going to be on the bottom. I need this solution where I have a big disc free and a peg to put it on. So you can take the Tower of Hanoi and look at how people break things down into sub-goals, which is called a means-ends analysis, and study the moves that they make. Some other types of problems where we don't necessarily know the rules, or maybe we don't know the start state, maybe we don't know the goal of the problem. So where you're not sure about the different parts, it's called an ill-defined problem. And there are some types of ill-defined problems where you'll have a sudden aha moment. Those are called insight problems. Despite all of the things that you're not sure about, you'll suddenly get the answer in a flash. So insight problems are a type of ill-defined problem. So I would say that college, while it seems like a very well-defined problem, here's my start state, no credit, here's my end state, all credits, here are all the rules, it's actually more of an ill-defined problem, because while your start state and your goal state can be clearly defined, there's still a lot of variables that you're not sure about, like what do you want to do with your life kind of variables. So some examples of some ill-defined problems, because they're fun. How can I cut this cake into 8 pieces using only 3 cuts? Okay, so the solution is, to cut the cake in the traditional X pattern. So that only gives me 4 pieces, and then I'm going to cut the cake horizontally to make my 4 pieces 8. That's a non-traditional solution, so it is an operator, a rule you didn't realize that you had. So I have a clear start state and a clear end state, but the end state's not totally perfect because I didn't realize I could cut it sideways. Another famous example, I have 4 pieces of chain, so these are my little pieces of chain down here at the bottom. And each piece has 3 links. She wants to make a bracelet, a full closed chain. How can you do that with only 3 openings of a piece and 3 closings of the pieces? What most people try to do is open and close, let's say these 2 together, open and close these 2 together, and then open and close these 2 together. But you're left with one long piece rather than a chain. So what you actually have to do is open and close one whole set of groupings and link those 3 together. You can ignore the bottom one because it's about money. I made it a little simpler than that, but the idea is that you have to think outside the box to be able to solve this particular problem. This is the famous 9-dot problem. So you have to connect all 9 dots with 4 contiguous lines, meaning you cannot pick up your pencil. Right? So the solution to the 9-dot problem is that you have to think outside the box, literally. So you have to go outside the lines to connect all of the dots. If you ignore my terrible drawing. Okay? You can't stop inside the dots. This is called the any problem. So you're supposed to name a commonly used 4-letter word ending in E-N-Y. This works much better if you say it out loud rather than having the problem on a screen. And if you ask people as the any problem, which is the way that that would be pronounced in traditional letter spellings, people have a really hard time with it. You can see with them running it through their head. Benny, Senny, Denny, Finny, and they're trying to figure out the alphabet. The issue is that the answer is deny, which is pronounced in a non-traditional sound of spelling rules, and so people have a hard time getting it. And then last but not least, my absolute favorite, the F problem. So there's only one word in the English language where the letter F does not make the traditional F sound. Okay. And that's the word of. People have a really hard time with that one. Almost no one gets it. Okay, so those are insight problems, ill-defined problems. So how do people study this? Well, one way is to look at problem space theory. Okay, so this is Newell Simon coming back to the artificial intelligence dudes we talked about in the first chapter. And they had a book called Human Problem Solving in which they sort of outlined this theory. And so they said that problem solving is a sort of like a work desk where you have all the different states. You have a start state and an end state. And you're sort of watching people move through that space as they work through the problem. So I have an initial state, and then all the possible intermediate states, and then a goal state. So the problem space is a set of choices from the initial state to the goal state. And a search tree is a representation of all those states laid out by applying operators. So this works really well for fairly simple problems. So why would we use this? What you can do is it's sort of like a GPS system. You can look at all the possible routes to solve a problem. So I can look at all the different things that you can do. I can see what's the shortest solution to the problem and whether or not people take that. And I can look at all the errors people make and whether or not they're willing to back away from an error. So the reason that we use this problem space theory is that it's sort of a nicely laid out way to study well-defined problems. So here's the problem space for the Tower of Hanoi. You have my initial state, come on little pin, and my goal state. So the shortest solution is to work your way down this way. But what you'll see people do is they'll work their way this way, and then sometimes they can cut over and then work their way down. So I can look at the errors that they make and then the path to the solution that they take. So it's a nice way to study well-defined problems. The big limitation with this theory is that often, even if you could map it out, so think about how complicated chess is, and they've mapped this for chess, but it required a lot of computing power, and that's how the games play chess against you, right, depending on what level you set it at, is that humans don't necessarily see the entire problem space. So we can't see all of the options available to us, and this theory sort of assumes that we could. People are not always the brightest, so we might have a limited selection of operators. So some operators are available to us, some of them are unknown. And we can't necessarily move from any one state to another, so we're sort of limited by the fact that we don't know what all of the operators are. So problem space theory really works well on the experimenter end. We can see what people do and make guesses about problem solving based on the paths they take. But on the person end, it doesn't really seem to satisfy the explanation of how people think about problem solving. And then it most certainly does not work for ill-defined problems or very complex problems.